So we came out with this formula. Basically allows us to determine if we know VI, VF, and delta T to determine how far that something's going. But I'm going to put another formula up here, and I'm going to ask you on this one to trust me. I could work it out and show you where all this comes from, but I doubt you really would remember, and it's something that you don't really need to worry about. Okay? All that's important is that formula itself and what that formula is telling us. So I have a second formula for delta x that looks like this. Delta x equals VI times delta t plus 1/2 a times delta t squared. Okay? So notice it solves for the very same thing. You're still solving, if you use this equation, you can still solve for how far that something will move. There's one big advantage to this formula over the previous one. So for instance, let's say that I'm dropping something, and I want to know how far did it move during the time that it was falling? How far did it move vertically when it was falling? Well, if you think about it, if I'm dropping this, what would my initial velocity, my first velocity, be if I'm just letting this go? I'm not throwing it. I'm just dropping it. What would my VI be in that case? Well, my VI would be 0. Think about what that would do to these formulas. So I would say if VI is 0, what I would get out of this, what would be left over if VI went away right here, I would have delta x equals 1/2 VF times delta t. So it's basically the distance it would move would be half of its final velocity times however long it's been falling. This equation would become delta x equals, this VI again would go away completely, and so would the delta t. This whole term would turn into 0. So it would equal 1/2 a acceleration times delta t squared. Now, which one am I going to use if I'm working a problem? I'm going to use the one that's easiest, the one that matches the units that I have. Let me explain why this would be a big deal. If I'm dropping something, all right, do I know how fast it's moving usually when it hits the ground? That's not something that's easy to determine how quick is it moving when it hits. So the disadvantage to this equation here is I have to know VF. I have to know it. What about this equation? Well, I have to know A together with the time. Do we know A if we're dropping something? It's a constant. It's basically A, you know that this is gravitational acceleration. We know what that is. All right? This is the actual number. It should come out to right around 9.81 meters per second squared. But what we usually use is 10 meters per second squared. So that means if I want to know how far something is or how high something is off the ground, all I really need to know is how long did it take to fall, the distance that you're measuring. Because this is a constant I can plug in right here. All I need to know is the time. If I know the time, I square it, and then multiply by 10 and multiply by 1/2. And I'm going to be able to solve for that. I can figure that out. If I want to know how high a cliff is, I drop a rock off the top of the cliff. If I have my cell phone, it's got a stopwatch on it, then I time it. Multiply by 10, multiply by 1/2, and square that time, and I know how high that cliff is. Okay? It's a fairly easy thing to do, and we're actually going to prove that out to you, hopefully, show you that physics does work by dropping something off the bleachers. All right, so now we're going to use the formulas that we've been going over, and we want to try them in real life because we want to make sure that all these things we're talking about actually work when we get out of the real world. So So what I have right here is I have a screwdriver. I'm going to take and drop this from the top of the stands over here, and using one of our formulas, we should be able to determine, if we just know how long it took to fall to the ground, we should be able to determine how high up that I am right now. So we're going to do that. We're going to use physics to determine the height of the bleachers here, and then I have a measuring tape that we're going to check it with. All right? Here we go. So we're going to drop 3 times. We're going to do 3 trials, and then we'll kind of figure out what the average height is for each one of those trials. All right, I'm going to drop from the very top of the fence right here, and then I'm going to stop it once I see it hit the ground. 3, 2, oops, let me get that reset. 3, 2, 1, drop. 0.98 seconds. 0.98 seconds. All right, second trial. Here we go. 3, 2, 1, drop. 1.03 seconds on that one. All right, trial 3. This is the last trial. Here we go. 3, 2, 1, drop. 1.03. 1.03. So let's use some physics and see if we can't figure out how tall that those bleachers are. So remember, we dropped that from the top of the fence that's on the bleacher, and we dropped it all the way to the ground. And so what I would really like to know is, what is this distance right here? I'm going to call it delta y. Okay, I'm going to call it delta y. I know we've been using delta x in many of the formulas that we've looked at. This is a distance just like delta x is, except it's in the y direction. It's vertical. Okay? You can treat it the same other than that. All right, so let's think about what we know here. And remember, there are 5 variables for any problem that deals with motion. They are VI, VF, A, delta, we'll call it delta y in this case, and delta t. So anytime I go into a problem that's like this, that involves motion, I always know it's going to be these 5. I write them right off the bat. I'm going to write them down right in the beginning, because this tells me that this is the stuff that I'm looking for. Okay? So let's take these one at a time and ask ourselves, do we know what that value is, or do we not know what that value is? So VI, the velocity, the moment that I released that screwdriver, did we know what that was? We did. I released it from rest, which means this is 0 meters per second. Okay? So 0 meters per second is what my VI is. Did I know what the VF was? So there's my VI. My VF would have been the speed the moment the screwdriver hit the ground. That would be my VF right there. Did I know what that was? Did I know how fast it was moving the moment it hit the ground? I had no way of knowing that. So I'm just going to put a couple question marks there. Do I know what A is? The acceleration that the screwdriver experienced. That's just gravitational acceleration, which we know is, I'm going to go ahead and use 9.81. That's closer to the exact number as opposed to 10. That's meters per second squared. And it's downward. That acceleration is always downward. So I'm going to say that it's negative, because I'm going to say that downward motion is negative. Anything then that moves up has to be positive. Do I know what delta y is, what that distance is? I don't. The fact is, if I'm trying to figure out how tall they are, that's my big unknown. That's what I really want to know. Okay? How about delta t? Did I know what delta t was? Well, I had my stopwatch on my cell phone out. That's what we were measuring. The 3 trials that we did, we're going to go ahead and average those. I had one that was 1.03. I had a second one that was 1.03. These are all seconds. All right, and I had one, I don't know what I did there, but 0.98 seconds on the third one. I'm going to go ahead and average all three of these, okay? If I add 1.03, 1.03 again, and then 0.98, 1.03 plus 1.03 plus 0.98, I get 3.04. Since there's three numbers, I'm going to divide by 3 to get an average. And that gives me 1.013 repeating. 1.013 repeating. And that's going to be what I call my delta t. Okay. So, how do I pick a formula? I've identified what I know. I've identified what I had, what I didn't. I can see right now that I know 3 of these 5. I'm going to be able to solve. As soon as I know that I have 3 of the 5, I know I'm going to have an equation that'll do it. How do I pick which equation will do it? Here's where knowing what you don't have comes in. You see, there's 2 things I don't know. But one of these 2 things I really want to know. It's this. That delta y is what I really want. I don't know what VF is, but you know what? I don't care. It doesn't matter for purposes of this, so I don't care. I'm going to look for an equation that says no VF right next to it. Meaning, if I have no VF, I'm going to use that equation. Now, if you look at your formulas in the back of your comp, the equation that is the no VF equation is the one that looks like this. And I'm going to use delta y instead of delta x. I believe that's the one that's in the back of your comp that was labeled no VF. Okay? Now, I wanted to solve for delta y, or the height, so I don't have to do any algebra at all. You got to love that. What I did know here, though, is that my VI is 0. So that means if this is 0, it doesn't matter what delta t is. This term is essentially just going to go away. It's going to turn into 0. And I end up with delta y equals 1/2 a times delta t squared. Okay? Again, I don't have to do any algebra. And if I check my units, seconds, these are in seconds, these are in seconds, both the distances are in meters. I don't need to convert any units. I can go ahead and plug in. Okay? Just plugging in my values is all I did here. So my delta y then is going to equal I'm going to say 1.013 times the same number because I got to square it. All right, that's going to give me 1.026 times 9.81 divided by 2. I get 5.03 for my answer. 5.03. Let's look at units here. When I square this, I get second squared. This has second squared in the denominator. So that means these second squared are going to cancel out those. What am I left with? I'm left with meters. And also, by the way, that's a negative, so should this be. So the answer that I got by taking a few measurements was negative 5.03 meters. All the negative means, you guys, again, is that it's moving downward. It ended lower than it started, which is how the screwdriver behaved. So our calculation here for the height of the bleachers then is 5.03 meters, or 5 meters and 3 centimeters, just a little bit extra. All right, so now what we're going to do is I'm going to use a tape measure, and we're going to actually measure this height. Hopefully the numbers that we use to calculate, we come up with a height here that is the same as the one that we measured. It's a little bit breezy today, so we have to have someone else hold it. All the way to the ground. All right, we have 4.83 meters. 4.83 meters.
Is it tight?
Hold it tight down there. Yep, 4.83 meters is the height with the tape measure. So we noticed just a little bit of a difference. What we calculated based upon the drop time of the screwdriver was 5.03 meters. What we actually got was 4.83 meters. That's about a 5% error in there. But if we understand physics, we can even explain the difference that's here. Remember, I used this value right here, which is the accepted value for free fall acceleration. The issue was our screwdriver, as it fell, was our screwdriver really experiencing real free fall acceleration? It wasn't. We don't have the possibility of getting rid of air, thankfully, in our environment. And so we had air. Let's think about what that would do. Without air, I would get this acceleration. All right, I would accelerate downward at 9.81 meters per second squared. With air, though, remember what's going to happen is as the screwdriver falls down, it has to take these little air molecules that are in its way, and it has to shove them out of the way in order to go into the space that they're in. So what does that mean? That means this air is going to exert a little bit of force upward. Okay, it's going to exert a little bit of force upward on that screwdriver. Not a lot, just a little bit. But what will that mean about the rate at which it accelerates? It won't accelerate as fast as what we wrote here. This number here would be a little bit lower. And if that number was a little bit lower, this number would be a little bit lower. Maybe giving you an answer that looks like this. All right, so the difference, this should be a little lower than what we would measure here because we got rid of air resistance with this number, and we can't. We'd actually have to have that air resistance in, which would bring this value closer to this one. All right, so hopefully you've seen physics does work. You can use these formulas, and you can find that situations are oftentimes a lot more predictable than you think they are.